Welcome, I'm Dr. Pauline Fu. In this video, I will conduct hypothesis test for 3 or more population means using analysis of variance ANOVA. There are two objectives. One is to verify the requirements for one-way ANOVA test. One way means one factor. The second objective is to conduct hypothesis tests for 3 or more population means using one-way ANOVA. ANOVA represents one-way analysis of variance. ANOVA, or analysis of variance, is an inferential method used to test the equality of 3 or more population means. When you compare 3 or more population means, the null hypothesis is population 1 mean equal to population 2 mean equal to population 3 mean. You cannot do this test by conducting 3 separate hypothesis tests. The reason is you are making a bigger type 1 error. Okay. The requirements for one-way ANOVA test: 1, there must be k simple random samples. And those k samples are independent of each other. Populations are normally distributed, and populations have the same variance. The null hypothesis is all 3 population means are the same. So this is the picture of H0. H1 alternative said at least one population mean is different from others. This is one picture showing H1. H1 could have other situations. For example, H1 could have mu1 equal to mu2, but not equal to mu3, or mu2 equal to mu3, but not equal to mu1. And this picture shows mu1 not equal to mu2, not equal to mu3. Now let's do an example to check the requirements for ANOVA. The following data represent the weight of pennies minted at Denver Mint in 3 years, in 3 different years, 1990, 1995, and 2000. Verify that requirements in order to perform a one-way ANOVA test. So this example only to verify the requirements. Next example, we will conduct ANOVA test. So this is the data, okay, 3-year data. So verify the first one. 3 samples are simple random sample. This one we assume, okay. How do you produce simple random sample? We did that in lecture 1. Okay. The second one, samples are obtained independently. Okay. This is obvious because when you pick one sample minted in year 1990, it is independent with another sample you pick from year 1995, and it is independent with another sample you picked from the year 2000. 3, normal probability plots for those 3 years are here. Okay, this is for year 1990. Normal probability plot roughly along the straight line, roughly. That means normality is met. And for year 1995, those are the probability plot. Those dots are the probability plot. And they're close to this straight line. So normality is met. And for the year 2000, this is the probability plot. Okay. Again, they're roughly to this straight line. So normality is met. Okay. So we verified 1, 2, 3. Okay. And for number 4, how do we verify the variance for 3 populations are the same? Okay, we can use a simple method. We can first calculate the sample standard deviations. Given a sample data, you can calculate standard deviation. Okay, and then we found the largest standard deviation is not more than twice the smallest standard deviation. If this is the situation, that means requirement of equal variance is satisfied. The largest standard deviation is not more than twice the smallest standard deviation. And this is the descriptive data. Okay. We have 3 years. Those are the variable. Okay, sample size n. Okay, sample mean, median. Okay, standard deviation, standard error mean, minimum, maximum, 25th quarter. This is 75th quarter. So this example shows all the 4 requirements are met. Next, we introduce F-test statistic. It is just a formula. It is the ratio between sample variability and within sample variability. It is the ratio. So, okay. Between sample variability, we use mean square due to treatments. There is a formula for this one, mean square due to treatments. And for within sample variabilities, we use mean square due to error. Again, there's a formula. Okay. So mean square due to treatment, the formula is MST. I will show you formula in one moment. The mean square due to error, the formula is for MSE. So F equal to MST over MSE. Okay. So between sample variability over within sample variability, the bigger the F value, the bigger the chance we will reject H0. Remember what is H0? H0 said all 3 population means are the same. So now this is example 2. Compute the F statistics and then make conclusions. Okay. Actually, the title should be test a hypothesis regarding those 3 population means. But this example actually just calculates the F-test statistic. So how do we calculate test statistic? First, you do the average for all the data. Remember how many total data here? So do calculation for the average of all these data. So there are 33 data here. Okay, so you add them all divided by 33, and that is your X bar, step 1. Okay, H bar, add all data together, divided by 33, and you get 2.5018. Step 2, found the sample mean for each treatment. Remember, we have 3 treatments, 1990, 1995, 2000. Okay, so sample 1 average 2.4964, sample 2 average 2.5091, sample 3 average 2.5. Okay, so that is step 2. How do you do the sample average? This is sample 1. Okay, you add them all divided by 11, and you get x1 bar, sample 1 average. And this is sample 2 average. Add them all, divide by 11, x2 bar. And this is sample 3 average. Add them all, divided by 11, okay, x3 bar. So you did the sample average. Okay. Next, calculate the sample variance for each treatment. Variance. Remember what is the variance? You use individual data x minus sample mean square it. You do this for each and every data. Add them all, divided by n minus 1. You get sample variance. This is for sample 1, year 1990. By the same token, you can calculate sample variance for year 1995 and for year 2000. Okay, I actually copied the original data in Excel. You can quickly do the sample mean and sample variance using Excel. See, this is the data. Okay, if you do the sample mean, I will put the result here. Maybe I will highlight so that this is not part of the data. This means sample 1 average, so equal average. Okay, so you get 2.49. So I'm doing average now, 2.49, okay, 64. And then you just use fill handle to produce average for the other 2. Okay, one is 2.5091 and the other is 2.5. So this is the average. Now, using Excel, you can also easily calculate variance. So I'm going to put the variance here and use different color to distinguish. Okay? So variance, you do var dot s means sample variance. Okay, so select those data. Okay, this is the sample 1 variance. Okay, and use the fill handle. You go to 3 variance. Okay, it is just rounded up to the 4th decimal places, the lecture notes. So this is the variance compared with these 3 variants. Okay, so as you can see, Excel is a powerful computational tool. Okay. So once you have the mean, the variance, so we do this one here. Sum of square due to treatment, SST. SST due to treatment, okay, means we use the sample 1 mean x1 bar minus the overall mean x bar. Remember the overall mean x bar is 2.5018. Means you add all the 33 data together, divided by 33, that number is x bar. And remember, we also produced sample 1 mean x1 bar, okay? And this one here is x2 bar minus sample 2 average minus overall average. And this number here is a sample 3 average minus overall, okay? And you have to square it. then times how many data in each sample. Each sample we have 11 data. Each sample we have 11 data. And then add them together. That is the sum of square due to treatment. Sum of square due to treatment. And this number is 0.0009. Okay. Next, we'll produce sum of squares due to error, SSE. Okay. And how do you compute SSE? Remember we did sample 1 variance, S1 square. Sample 2 variance, S2 square. Sample 3 variance, S3 square. You use sample 1 size minus 1 times sample 1 variance plus sample 2 size minus 1 times sample 2 variance plus sample 3 size N3 minus 1 times sample 3 variance. You add them together, that is the sum of square due to error. Okay, and the result for this example is 0.013. Once you have SST, SSE, you then compute the mean square due to treatment, MST. You use SST divide K represent number of treatments. In our example, K equal to 3 because we have 3 different years, 1990, 1995, and 2000. Okay, and you do the calculation, you get MST is this number, 0.005. And then MSE is the mean square due to error. You use SSE divide N is total sample size 33 minus K. K is the number of treatments, and you get this number. Okay, and the test statistic F is just the ratio between MST and MSE. Two numbers, you do the division, you get F test statistic, and the result is 1.25. Okay, so you get this F test statistic. Okay. And once you get this F test statistic, how do you make conclusion? But this example is not about hypothesis test, rather it is about how do you compute F test statistic. Okay, if you want to make decision, you have to calculate critical value for F, that is out of the range of this lecture. Okay. But you need to know the large value of F suggests sample means for each other is different. Okay. And now I'm going to show you the Excel to conduct ANOVA test and to make decisions. Okay. So this is the data. Okay, original data from here to here. Using Excel, I can do one-way ANOVA test. So I go to data analysis, ANOVA, single factor. The factor is based on year. Okay, click OK button. Input range, select A1 to C12. As you can see, I include labels in the first row, grouped by columns. Alpha is 0.05. Output range, I will put in E1. Okay, and then I click OK button. So this is my ANOVA summary table. Okay, so now I'm going to analyze this one because I want to make annotation. So I'm going to copy this one into OneNote somewhere here. So that I can make annotation. Okay. Make the font bigger. And when you have this output, how do you make decision? How do you know three means are the same or different? Oops. Try to move this along. The easy way, check out the p-value. Okay, see? P-value is 0.34. When p-value, this number greater than 0.05, greater than alpha. When p-value greater than alpha, you reject H0, reject. Remember what is H0? H0 said all the three means are the same, you reject in favor of H1. Remember what is H1? H1 said at least one mu is different from others. Okay, so that is the p-value method. And you can also get the test statistic here. This is test statistic. Okay, and this number 0.004, this is a MST. Okay, this number is MST, mean square due to treatment. And this number here is MSE, mean square due to error. Okay, and over here you have SS, this number is SST, sum of square due to treatment. And then you have this number is SSE, sum of square due to error. We did those calculations by hand, but Excel can help you get those calculations. Okay, all right. So in summary, what I did in this lecture, we did the requirements for conducting ANOVA test. There are 4 requirements. And then we calculated test statistics, both by hand and by Excel. We also actually did a hypothesis test based on the p-value to test if 3 population means are the same or at least one population mean is different from others. That's all for this lecture. Thank you so much for your time. I look forward to see you next time.